Yes, good morning, dear students. Welcome for the physics class. Previous class we have discussed about the resistivity, and just in this class, I want to explain the resistivity of a metallic conductor varies with the temperature. Okay, so already in the previous class we have discussed that one. As the temperature increases, the resistivity also increases. Now in this class, how the resistivity of a metallic conductor is going to increase with increase in temperature, or else decrease in with the decrease in temperature. According to what expression it is going to happen, so we have to see. Okay, so look here, the resistivity of the metallic conductor is going to vary with temperature according to this formula, that is rho T is equal to rho 0 into 1 plus alpha into T. Okay, according to this equation, the resistivity of the metallic conductor is going to vary with the temperature. So here, rho T is, it is the resistivity of metallic conductor at temperature T degrees Celsius. Okay, resistivity of metallic conductor at temperature T degree Celsius. Okay, and then rho naught means it is also a resistivity of conductor at 0 degree Celsius. At 0 degree Celsius. And alpha means it is the temperature coefficient of resistivity. Alpha means it is temperature coefficient of resistivity. Okay, so here this temperature coefficient of resistivity is positive for the metals and alloys. Temperature coefficient of resistivity, the alpha value is positive for metals and alloys, and it is negative for semiconductor, and it is negative for the semiconductor, because as you can see here, resistivity of the metallic conductor increases with the temperature, but as we go for the semiconductor, the resistivity of the semiconductor decreases with increase in temperature. Okay, that means in case of the semiconductor, the resistivity is inversely proportional to temperature, but in case of metallic conductor, the resistivity is directly proportional to the temperature. So that's why the temperature coefficient of resistivity for metals and alloys is positive, and for that of semiconductors it is negative, because in case of semiconductors, resistivity is going to decrease with the temperature. If you want to represent that for semiconductor, the resistivity decreases with temperature with the help of graph, then the graph will be like this. So along the y-axis, I take the resistivity. Okay, along the x-axis, I take the temperature in degrees Celsius. If the temperature increases, then the resistivity is going to decrease. It is for semiconductor. Okay. For metal, the resistivity will increase for metals and alloys. So for example, I consider copper. Copper is a metal. Okay, metallic conductor. So the copper, look here, resistivity and temperature in degree Celsius. How in the copper, how resistivity supposing move like this. Okay. As temperature increases, resistivity also increases. At 0 degree temperature, whatever resistivity the copper is having, that is we can denote it as rho naught. Rho naught. Okay. Okay. For other alloys, I'll just consider nichrome. Nichrome, you can take nichrome, manganese, and constantan. So for these materials, manganese, and constantan, nichrome also. And constantan. How the resistivity of manganese and constantan and also nichrome vary with the temperature. So here the temperature in degrees Celsius and the resistivity. So here in this case, the resistivity is going to increase with the increase in the temperature, that is a linear manner. Okay. If the temperature increases, the resistivity also increases linearly. Okay. So here at 0 degree Celsius, whatever resistivity the magnet and constantan have, that we can call that rho naught. Okay. As you can look here, the straight line, the variation of resistivity with respect to temperature for magnet and constantan is given by the straight line. So that is nothing but as the temperature increases, the resistivity also increases linearly. As temperature increases, resistivity also increases linearly. Okay. Next one is why is it so? Here you can see the resistance suddenly rising faster and increasing the temperature, but here the resistivity is increasing linearly with increasing temperature. Why? Because here the temperature coefficient of resistivity for manganese and constantan is a very low. Alpha value is very low. Okay, and the effect of change in temperature, on these materials is slightly less affected. Okay, slightly less affected. This resistivity of manganese and constantan is slightly less affected on changing the temperature. Okay, because temperature coefficient of resistivity is less. Okay. Next concept is conductors. And this conductance is going to represent the help of G here. Okay. So what do we mean by conductance? Conductance is nothing but the reciprocal of resistance. Okay. So conductance is reciprocal of resistance, 1 by R. So what is the SI unit of conductance then? So SI unit is, look here, resistance assigned is ohm. Here resistance is as a denominator. Okay. Then 1 by ohm means per ohm. Per ohm. This is the SI unit of conductance. And symbolically we can write ohm means small is omega to the power minus 1. Or else one more unit we are having SI, that is Siemens. Siemens is the unit of conductors. So next comes conductivity. Conductivity, it will be represented with the help of sigma. Conductivity is reciprocal of resistivity, that is 1 by rho. Then what is the SI unit of conductivity? The SI unit of conductivity means a resistivity SI unit is ohm meter. It is in the denominator, so that's why per ohm per meter. Okay, per ohm per meter. So it can be indicated by symbolically per ohm per meter. Or else simply look here, per ohm is nothing but Siemens. Siemens means it is indicated by S. Okay. So here also instead of per ohm I can write Siemens per meter. Siemens per meter. It is the SI unit of conductivity. Is it clear? So next concept is the drift velocity. Next one is drift velocity. So here drift velocity is going to represent symbolically as a V subscript D. So what do you mean by drift velocity? So it is the average velocity with which the free electrons, here it is the average velocity with which the free electrons inside the metallic conductor were going to drift in the opposite direction to the electric field when a potential difference applied across the ends of the conductor. So it is the average velocity with which the free electrons drifted in metallic conductor opposite to electric field when potential difference is applied across ends of conductor. What it means? So for that we have to consider a diagram where I consider a cylindrical shaped metallic conductor, or you can consider it as a metallic wire. So here we are having the fixed ions, right? So here these are what? Fixed atoms or positive ions. Fixed atoms or positive ions. So it is a free electron. Okay. So initially it is at rest. Here we are not applying any potential difference. Initially it is at rest. So now I am going to connect a battery across the ends of the conductor. I am going to connect the battery across the ends of the conductor in order to create a potential difference across the ends of the conductor. So So it is plus and minus. Here it is a battery, and when I connect the battery, what happens? The electric field will be set up inside the conductor because this terminal will become positive. This terminal of the conductor becomes a positive because it is connected to the positive terminal of the battery, and this end of the conductor becomes a negative because it is connected to the negative terminal of the battery. Okay. So now it is a positive terminal, it is a negative terminal of the conductor. Then what happens? Positive and negative has been separated with certain distances. Electric field will be generated inside, will set up inside. So what happens? That electric field is going to accelerate these free electrons in this direction. Means free electron is going to accelerate in the opposite direction to the electric field. Electric field direction is from plus to minus. So here electron will move from minus to plus. Okay. So look here. When it moves, it is going to collide with the atom, and again it changes its direction, and again it will move. Is it clear? So whatever acceleration has been produced by the electric field which is set up inside the conductor, okay, that acceleration will drift the electrons in the opposite direction to the electric field. So here the average velocity with which the electron has been, free electron has been drifted in the opposite direction to the electric field, and that average velocity is called as drift velocity. I hope it's clear to you. Okay. The next one, relaxation time. Relaxation time. So is given by tau, right? So what do you mean by the relaxation time? It is the average time interval between two successive collisions. Okay. It is average time interval between two successive collisions between electrons and fixed atoms or fixed positive ions. Just here, two successive collisions means the first it will collide here, and then it will collide here. And it will take some time to collide from here to here. Okay? And again here, from here it has been collided, and again from this, it is going to collide somewhere here. Okay? And the time interval between these two successive collisions. So likewise, all the times we need to take average. So it is average time interval between the two successive collisions between the free electrons and the fixed atoms or ions. Okay? And it is going to be given with the help of tau. It is average time interval between two successive collisions between free electron and fixed atoms or positive ions. Fixed atoms are positive ions. This is about the relaxation time. The next one is mobility of free electrons. Mobility of free electrons, and it is going to be represented with the help of mu. Okay, mobility of free electrons means it is the drift velocity acquired by the free electrons per unit electric field. Okay, this acquired by free electrons per unit electric field. So that is mu is equal to Vg divided by E. And the SI unit of mobility is nothing but meter square per volt second. Meter square per volt second. Okay, it is the SI unit of mobility. Now next we are going to have the expression for drift velocity.